Hello. In this video, we're going to talk about inverse trig functions. Now, there's not a specific section in your textbook that addresses all these notes, but I have given you a handout, so if you want to get your handout out, we can go ahead and take a look at these few concepts. The first thing, of course, is our motivation. Why are we studying inverse trig functions? What's the idea here? And the question we want to answer is, what is the derivative of sine inverse x? Now, we know the derivative of sine x is cos x, but what about sine inverse? And in particular, what even is sine inverse x? You might have seen the button on your calculator when you do sine -1, a second function sine, but what really is this operation? What does this function look like, and how do we take its derivative? So to do that, we actually need to figure out what the graph of sine inverse x looks like and spend a little bit of time learning about inverse trig functions in more depth than you might have learned in pre-cal. So let's start with a few definitions. If you remember from pre-cal, a function, f, which maps from a to b, is one-to-one if it passes the horizontal line test. So a one-to-one function is a special type of function. All functions have to pass the vertical line test. So if you remember, that's when you have a vertical line going across the graph, and it can only intersect the graph at one point at most. So all functions have to pass the vertical line test, but there's a special type of function that also passes the horizontal line test. And these functions are called one-to-one. And they're special because if a function is one-to-one, then there exists an inverse function. And we know one thing about inverse functions: f inverse of f of x is simply x. This should make sense because the inverse is undoing the function. It's like doing the opposite. So if you do the function and then do the opposite of the function, you just get back where you started. Now from pre-cal, you should remember that the graph of f inverse is the mirror image of the graph through the line y equals x. In other words, it's the reflection across the line y equals x. Since only one-to-one functions have inverses, or proper inverses, inverses that are functions, if f of x is not one-to-one, then what we tend to do is restrict its domain to make it one-to-one. You might remember this again from pre-cal, where we took a function that didn't have an inverse, we restricted its domain so that it did. Let's look at a familiar example. Suppose we have the function x squared. Now, of course, this is indeed a function, because if we look at vertical lines going across the function, we see that a vertical line only passes one point. But if we start trying to draw horizontal lines, we can see right away, a horizontal line here is going to intersect the graph at 2 points, which means this function is not one-to-one. Very unfortunate, very unfortunate. I was hoping it'd be a one-to-one function, but it turns out it's not, because it is not passing the horizontal line test. But we could make this function one-to-one. In particular, this left half of the function over here, it's not really needed. So instead, we're going to chop it off, and we're going to just reduce the domain to 0 to infinity. Well, now if we look at this graph here, we have a wonderful one-to-one function. Imagine that horizontal line test. Anywhere you draw a horizontal line, you're only going to intersect the graph at most one time. So this graph is 1-to-1. And because it is 1-to-1, we can determine an inverse. So a quick clicker question for you here. Which of these graphs is 1-to-1? A, B, C, or D? I'll give you a second to think about it. All right, hopefully you've come up with an answer. Let's take a look. It's definitely not A, because if we draw a horizontal line, it intersects 2 times. It's definitely not C. Again, if we draw a horizontal line, we have 2 points of intersection. Definitely not D. My goodness, we have 1, 2, 3 points of intersection. But if we look at drawing any horizontal line on B, we're only going to get 1 point of intersection. So the answer is indeed B. B is 1-to-1. Popping back to our original question, y equals x squared, if we're going to determine the inverse, you might remember from pre-cal, you go ahead and take the equation y equals x squared and you swap x and y. Then you go ahead and solve for y. So of course, if we have our equation here, x equals y squared, or y squared equals x, We simply square root both sides, and we get y equals square root of x. Technically, it's plus or minus, and we just take the positive version so that we have just a single piece of the function. And this would be our inverse. We have f inverse x equals root x. And you can see that f inverse of f of x will be equal to square root of x squared, which does equal x. Of course, we know it equals technically plus or minus x. But since x is on the interval, well, we're looking 0 to infinity, we only worry about taking the positive sign because we're only looking at positive values of x. So indeed, when we do the inverse of the function, we get back where we started. And so this is indeed the inverse. F inverse of f of x is x, and so the inverse of the parabola is the square root. That's review from grade 12. But what if we had a sine function? Let's consider sine x. Now, what do you think about this function? Does it look like it passes the horizontal line test? Does sine x look 1 to 1? Well, all you need to do is draw a short horizontal line and you'll see, oh no, we are definitely crossing the graph in more than one place. And so sine x, as it stands, is not 1 to 1. We should write that down. This is not a 1 to 1 function. But what if we do a little restriction? Well, we could restrict maybe from 0 to pi, but that wouldn't solve our problem. We can see right away that that's going to still give us 2 points of intersection. But what if we restricted from minus pi by 2 to pi by 2? Well, if we chopped it there and there, we'd get this following graph here. And this graph does look 1 to 1. This graph is 1 to 1. And so, yeah, this graph is going to be a 1 to 1 function, which means it's going to have an inverse. So the definition, this is very important, the definition of the inverse sine function, which we write sine inverse with sine -1, or we sometimes write arcsine. It's defined as y is equal to sine inverse of x if and only if sine of y is equal to x. And it has domain -1 to 1 with a range of minus pi by 2 to pi by 2. And it looks like this thing here. Well, where did that graph come from? Let's take a look on Desmos to understand this process a little more in depth. So here on Desmos, we have our graph y equals sine x, and we can see very clearly that it's not a 1 to 1 function. But if we go ahead and restrict it from minus pi by 2 to pi by 2, it becomes a 1 to 1 function. We then draw the line y equals x, and we think about reflecting this graph over that line. Well, we can see a lot of the graph lies very close to that line, and so a lot of it's going to look the same around 0, but we can see over here that there's going to be a little portion that's going to flip up and maybe look about this, and a little portion here that's going to reflect down over to here. And that's exactly what we find when we go ahead and graph the inverse function. It looks like that. And so we can see this nice little wiggle up here has been reflected from here, and the wiggle down here has been reflected over here. Now it's interesting to note that we had an original domain of minus pi by 2 to pi by 2, and the original range of the function of sine x was from -1 to 1. When we do the inverse function, we know that the domain and range switch. And so the domain now of our inverse function is from -1 to 1. And the range of our new inverse function is from minus pi by 2 to pi by 2. Let's take a look at a quick multiple choice question. Which of these graphs is the inverse of this graph? Either A, B, C, or D. Again, I encourage you to pause the video and give it a try yourself. Well, let's go ahead and take a look. A is actually the vertical reflection of the graph. So it's a reflection, sure, but it's not the inverse. And B is also a reflection. It's a horizontal reflection. D happens to be the same graph. So that's not really any type of reflection, but if you look at C, you can imagine this graph and the line y equals x C is the perfect reflection across that line y equals x. And so the answer for this question is indeed C. Just as a bit of bonus information, this graph here is an exponential. This graph over here is a logarithm. And we should remember from pre-cal that the inverse of an exponential is a logarithm. Now, how would you evaluate sine inverse of x? Because if somebody asks you to find this as a function and to start figuring out values, it might be a little bit tricky. Perhaps somebody says, find sine inverse of root 3 over 2. Especially without a calculator, this can be a challenging question. But here's how I tend to solve these problems. I first set it up as an equation. So I set up an equation as y equals sine inverse. And then I'm going to take sine of both sides. So let's see how that would look here. I start with y equals sine inverse of root 3 over 2. And then I take sine of both sides. So you can imagine taking a little sine here and a sine here. Sine of sine inverse, well, they're inverse functions, and so they cancel each other. Over here, you're just left with sine of y equals root 3 over 2. Now I have to think a little bit. I have to think about the unit circle. In particular, I want to ask myself this question. When I'm solving the equation sine y equals root 3 over 2, I'm thinking, what angle would give me this value? What angle do I need to get the value root 3 over 2? So think about that unit circle. Think hard. What angle on the unit circle is going to give me root 3 over 2 as the coordinate point? Again, this is a bit backwards from what you're used to. Usually you're given an angle and asked for the unit circle value. Now you're given the unit circle value and you're asked to go backwards for that angle. But if you think about it, you should realize that y equals pi by 3. Now, are there other values on the unit circle that might work to give you root 3 over 2 for sine? Sure, if you think about it, there might be another value that has root 3 over 2 as the coordinate for sine. In fact, if you think long and hard about it, you might find the value 2 pi by 3. But it's very important that we don't write that down, because when we're doing sine inverse, we only want to be looking on a particular portion of the unit circle. In particular, this is how we draw our unit circle for finding sine inverse. Here's our little unit circle, and we only draw it from minus pi by 2 to pi by 2. This is the only portion we look at because we restricted the domain. If you remember a few minutes ago, we chopped the domain of sine x to go only from minus pi by 2 to pi by 2. So we're only allowed to report values from this section of the unit circle. Looking back at our next question, sine inverse of negative 1/2. We set it up like before. Y equals sine inverse of minus 1/2. So sine of y equals negative 1/2. And you think about that unit circle. What value on the unit circle gives you negative 1/2? Well, the answer is technically 11 pi by 6, but we can't use 11 pi by 6 because that's not in the domain of minus pi by 2 to pi by 2. So instead we have to write y equals minus pi by 6. All of our answers have to again come from this section of the unit circle. Now let's go ahead and do the same set of steps for cos x because we'd like to find cos inverse. If you look at the graph of cos x, it's clearly not a one-to-one function. And unfortunately, we can't do the same restriction. If we were to go from minus pi by 2 to pi by 2, we would find that the graph is still not a one-to-one function. So that's not going to be any good for us. That's not going to give us what we need. In fact, if you look, we're going to need something like this. Maybe 0 to pi. Well, that starts to look one-to-one. And indeed, that's the domain we're going to restrict. We're going to restrict cos x to the domain 0 to pi and get the following graph. Next, we're going to define the inverse function. So we define the inverse cos function, denoted cos inverse or arc cos, to be defined as y equals cos inverse if and only if cos of y equals x, with domain minus 1 to 1 and range 0 to pi. Again, I'll pull this up on Desmos to give you a feel for what's going on. So here we have the graph of y equals cos x, and we can see that it's not 1-to-1, but if we go ahead and restrict it to just 0 to pi, we definitely have a 1-to-1 function. Now we draw the line y equals x, and we imagine reflecting the graph across that line. And we get the graph of cos inverse. This is a little bit more interesting, I find, than the graph of sine inverse. We can see that this little portion reflected down here, and now this long wavy portion reflected up here. Again, the domain of the original cos graph is 0 to pi, which makes the range of this new inverse from 0 to pi. Again, the range of the initial cos graph was -1-to-1, which makes the domain -1-to-1 for the new graph. Remember, domain and range are always swapping when you do the inverse. So let's get some practice evaluating cos inverse. How would you evaluate y equals cos inverse of x? Same as sine. You'd set up an equation, take cosine of both sides, and then think to yourself, what angle would give this value? So let's try the first one here. You're going to set y equal to cos inverse of √3/2. You take cos of both sides to give you cos y equals √3/2. Again, you can think about writing a little cos here and a little cos over here, and cos of cos inverse, well, they cancel out. Now you think to yourself, what angle do I need on that unit circle to give me √3/2? And the answer is y equals pi/6. Similarly, over here we have cos inverse equals -1/2. So we have y equals cos inverse -1/2, or cos of y equals -1/2. Now what angle do I need to get -1/2? Again, you need to be careful because we're only looking on a specific portion of the unit circle. For cos inverse, we draw our unit circle only like this. We're only looking from 0 to pi. That's the only section we're allowed to think about. But if we think long and hard, we will find the correct angle. Y equals 2 pi by 3. Let's look at another multiple choice question here. What would be arcsine, or sine inverse, of -√2/2? I'll give you a minute to think about it. Feel free to pause the video. So we need to think what angle is going to give us -√2/2 on the unit circle. Pi/4 is going to give us √2/2. 3 pi/4, well, that's still going to actually give you, for sine, √2/2. -3 pi/4, well, if you think about that one, that would give you -√2/2, but it's not in the interval we want. We're only looking for -pi/2 to pi/2. This is too big. But in fact, pi/4 negative, if you go backwards pi/4 on the unit circle, that will give you the angle you're looking for. So the answer is -pi/4. Let's try another multiple choice question here. What is arc cos of -1, or cos inverse of -1? I'll give you a minute to think about it. Well, for this one again, we want to draw our little interval that we're looking for. We're only focused on this portion of the unit circle, from 0 to pi. So right away, we can throw out minus pi. Now, 3 pi/2, same thing. We can throw that out. Those are outside the domain. We're only either looking at pi/2 or pi. At pi/2, we know cos of pi/2 is 0, so that's definitely not it. And so our final answer would be pi. We know cos of pi is equal to -1, so therefore arc cos of -1 is equal to pi. So putting it all together, we're going to run through all the inverse trig functions: sine, cos, tan, secant, cosecant, cotan, how we make inverse trig functions for each one of our 6 trig functions. And so in general, remember, a function is 1-to-1. If it is, we can define the inverse function as follows: f inverse of x equals y if and only if f of y equals x. Now, defined on the entire real line, the trigonometric functions are not 1-to-1. But if we restrict their domains, we can define inverses of these restricted functions. So y equals sine inverse, sometimes denoted y equals arcsine, is defined as, and here's the definition. If you're ever looking for the definition on a test or on an exam, this is what you write. Y equals sine inverse if and only if sine of y equals x, and x is an element of negative 1 to 1, y is an element of negative pi by 2 to pi by 2. This is where the function lies. How do you think about it? Well, you think if sine inverse of x is the angle in negative pi by 2 to pi by 2, whose sine is x. The graphs, we've taken a look at these already. Here's the restricted sine, and here's the reflection to make sine inverse with the appropriate new domain and range. This is the domain and range we write down when writing the definition. Part of the definition is to actually specify the domain and range, and so you need that as part of your definition. Well, let's look here at cosine. The same idea applies. We have the following definition. Y equals cos inverse of x if and only if cos of y equals x. X is an element of negative 1 to 1, and y is an element of 0 to pi. Again, you want to think about the angles in 0 to pi, and that's how you find your cosine. So here's cos of x, here's cos inverse of x. Again, with the new domain and range for this inverse function. Now, I particularly like the graph of tan inverse. I think it looks quite nice. Because tan, we don't really have to restrict it in a complicated way. We know that tan inverse is actually going to be a one-to-one function on its initial period from minus pi by 2 to pi by 2. It's just that the tan graph, we know that there's copy after copy after copy after copy of the original base graph. So we just don't draw any of those copies. We just draw the original tan graph, which goes on minus pi by 2 to pi by 2 with round brackets because of those asymptotes. And when we draw the inverse function, those asymptotes that were vertical become horizontal. And this nice, almost cubic-like shape becomes a sideways graph lying between those asymptotes. So for the definition of tan inverse, we have y equals tan inverse of x, if and only if tan of y equals x. X is an element of negative infinity to infinity, and y is an element of negative pi by 2 to pi by 2. Now the graph for secant inverse is a little bit trickier because secant, well, is just a bit of a trickier graph to begin with. Here's the definition. Y equals secant inverse of x if and only if secant of y equals x. And x has this very strange interval, negative infinity to negative 1 union 1 to infinity, and y has this strange interval, 0 to pi by 2 with round bracket, and then pi by 2 to pi, square bracket at the end there. Well, let's take a look at these graphs initially, and then we'll show on Desmos how we come up with them. So the graph of secant looks like this. If you remember from pre-cal, there's these little U shapes that go on and on and on for the graph. And so we can't actually take the full U shape here because it wouldn't be one-to-one. So we take half of one of the up U's and half of one of the down U's. Now that creates an interesting situation for us because if we look at this graph, it has a domain of 0 to pi except at that vertical asymptote at pi by 2, which means that the range over here is going to be from 0 to pi except at the value pi by 2, which is why we have these round brackets. These come from the vertical asymptote here. And of course, that vertical asymptote becomes a horizontal asymptote here. The domain of secant, or I should say the range of secant, which gives the domain of secant inverse, the range looks like it goes all the way down to negative infinity and all the way up to positive infinity. But there's this gap from minus 1 to 1, which creates this gap over here from negative 1 to 1 on the domain of secant inverse. We'll go ahead and take a look at Desmos to help further our understanding. So to graph secant, we have to actually graph cosine first. Hopefully you've seen the graph of secant in pre-cal, but if you haven't, here's a quick overview. You graph cosine, and secant we know is 1 over cosine. So the graph of secant is actually created by doing reciprocals. So we know that at 1 cos of sorry, at 0 I should say, cos of 0 is 1. And so when we do the reciprocal of 1, we get 1. Similarly at pi, cos of pi is minus 1, and the reciprocal of minus 1 is still minus 1. These are invariant points when you do the reciprocal. And then all these small values become big, and when cos becomes equal to 0 at pi by 2, we end up with a vertical asymptote. So that's how you generate the graph of secant. And so just removing the graph of cosine there, we have here our secant graph, which is these nice u's that repeat over and over. But we want to restrict it. We don't want all those u's. In particular, we only want it to be 1-to-1 because right now it's not a 1-to-1 function. So we restrict it and we get this nice graph that's clearly 1-to-1. We draw the line y equals x, and now we imagine, just think for a second, what would it look like if you reflected those two little half u's over the line y equals x? Well, hopefully your imagination would give you this. We can see here, this portion is reflecting here, this portion is reflecting here, and that line that was a vertical asymptote has now become a horizontal asymptote. The graph of cosecant inverse of x is very similar. So we have here the definition. Y equals cosecant inverse of x if and only if cosecant of y equals x. X is going to be on the interval minus infinity to minus 1, union 1 to infinity, and y is going to be in the interval minus pi by 2 to 0, union 0 to pi by 2. So again, what we have here is cosecant of x. Used to be, of course, more u's, very similar to secant, but we had to chop it from minus pi by 2 to pi by 2 to make sure we had a 1-to-1 function. Then we drew the line y equals x, and we created the following inverse function here, cosecant. Again, I'll show you on Desmos the process to help further your understanding. So if you remember, the graph of cosecant x comes from 1 over sine x. So you imagine doing the reciprocal to sine. We see that when sine is equal to 1 or minus 1, we have invariant points. All the small values of sine, become big values on cosecant. And when you have, in particular, intercepts, they become vertical asymptotes for the new graph of cosecant. So we can hide the sine graph for now and just look at cosecant. We see these nice U shapes. But clearly this graph is not 1-to-1. We need to restrict the domain to maybe something like this, minus pi by 2 to pi by 2. Now we definitely have a 1-to-1 function. It's passing the horizontal line test. We can grab our line y equals x, and we can imagine reflecting over that line. So again, I encourage you, just pause the video for a second. Try to imagine what that reflection would look like. Okay, hopefully you imagined something like this. The two little pieces that extend over the graph right here, the little pieces get reflected. And then these big portions here reflect down, and these big portions here reflect over here. And there was a vertical asymptote at x equals 0. It has now become a horizontal asymptote at y equals 0. For our final inverse trig function, we're going to look at cotan inverse, which looks similar to tan inverse. And we have the following definition. Cotan inverse of x, if and only if cotan of y equals x. X is an element of minus infinity to infinity, and y is an element of 0 to pi. So the cotan graph looks like this. It's very similar to tan, but it's a bit wiggly on 0 to pi, not minus pi by 2 to pi by 2. And then when you reflect it, you end up with cotan inverse with the domain minus infinity to infinity, and these asymptotes that are at 0 and pi become asymptotes at 0 and pi, now horizontal instead of vertical. So let's try a couple examples here. How would we calculate secant inverse of 2? Well, the same principle applies. We have y equals secant inverse of 2, or secant of y equals 2. Now, I tend to not memorize my secant unit circle. I don't know about you, but I like my cos unit circle a lot better, and I know secant is 1 over cos. So 1 over cos is 2, or if we do the reciprocal of both sides, cos of y is equal to 1 over 2. Oh, hey, I can think about the cos unit circle a lot easier than the secant unit circle. Where is cos equal to 1/2? What angle do I need? Well, I need angle y equals pi by 3. And so secant inverse of 2 is pi by 3. Now let's look at a bit of a more complicated example here. Apparently, we can express cosecant of arctan of x as an algebraic function. That seems a little bizarre, but this is a very important technique that we're going to use in the next lesson to look at the derivatives. So how would we do this question? What is it even asking? Well, apparently we're somehow able to reduce this. There's some type of algebra, some type of method to reduce this into just algebra. Apparently the trig is going to disappear. And here's what we're going to do to start. We're going to let y equal tan inverse of x. Tan inverse of x or arctan, they mean the same thing. Really what we're doing is we're setting this inside portion here to become tan inverse of x. Well, if we do that, our next step, of course, would be to take tan of both sides and get tan of y equals x, which I'm going to write actually as x over 1, because I know something about tan. In particular, I know from grade 10 that tan can be written as, well, SOHCAHTOA, opposite over adjacent. And so if I was to draw myself a little triangle here, I could figure something out. If this was a y angle, and I knew tan was opposite over adjacent, I could draw myself a little triangle with x and 1. Now what do you think? Could we find this missing side over here? Oh, of course we could. We use a little bit of Pythagoras' theorem. A squared plus b squared equals c squared, and we'd square root the c. So this side would be 1 plus x squared. That's fun. We fill in the little triangle. We have all 3 missing sides. But then you ask, okay, what was the point of that? Why are we drawing triangles? We're supposed to be doing something with cosecant. Well, let's go back to our original question now. We were asked to find cosecant of tan inverse of x. But tan inverse of x we called y. So we were trying to find cosecant of y. But cosecant means 1 over sine. And so cosecant of y, or 1 over sine y, means we're looking for, if SOHCAHTOA says that sine is opposite over hypotenuse, 1 over sine would be hypotenuse over opposite. Which means we're looking for this triangle. What is the hypotenuse and what is the opposite? Well, the hypotenuse is going to be root of 1 plus x squared, and the opposite is going to be x. So our final answer is the square root of 1 plus x squared over x. Now perhaps you think this is clever math magic and there's no way this is true, but let's take a look on Desmos. So here I have the graph of y equals cosecant of tan inverse of x. Looks a little bit like a reciprocal function, maybe a 1 over x, but not quite because the asymptotes aren't in exactly the right place. But now, let's go ahead and graph root 1 plus x squared over x. Apparently, I mean, maybe it's just me, but I can't tell the difference between those two graphs. They look identical, because in fact they are. When you do composition of 2 trig functions, not all trig functions, but particular trig functions, when you do their composition, you can sometimes end up eliminating the trig altogether and just ending up with a combination of radicals and rationals. It's quite a neat thing that happens in math, and we're going to need to use this type of solution when we get to the derivatives. But before we do that, we'll do another example with this algebraic trick because it's a little bit challenging. So let's go ahead and express cos of arc cotan of x as an algebraic function. Well, I'm going to do the same thing. I'm going to let y equal cotan inverse of x. I'm going to take cotan of y equaling x over 1. I'm going to draw myself a little triangle here. Here's my angle y. And cotan, if we remember, is going to be the reciprocal of tan. So if tan is opposite over adjacent, cotan is adjacent over opposite. So this is adjacent, and this is opposite. Again, the same bit of Pythagoras will give us this side as 1 plus x squared. And this is kind of work on the side almost. We now go back to the original question. So we want to find cos of cotan inverse of x. Well, that'll be cos of y. And cos, we know, is adjacent over hypotenuse, singing SOHCAHTOA. Adjacent is x. Hypotenuse is square root of 1 plus x squared. And I encourage you to pause the video and demonstrate to yourself, prove to yourself that using Desmos, if you type this in or you type this in, you get the same graph. Now for homework for this lesson, I want you to take a look at the graphs. You definitely should look over the graphs. Look over the graphs. You should know what the graphs look like in terms of basic shape, and you should definitely know the domain and the range. Maybe make yourself some little flashcards, because you definitely want to know those. As well, I would encourage you to look at the inverse trig worksheet. So it's a handout that was given called Inverse Trig Worksheet that gives you some practice using this algebraic technique, as well as just finding the basic values of inverse trig functions. Now before we end, a few clicker questions, a few multiple choice questions. How would you find arccotan of 1? Would it be 0? Would it be pi by 6, pi by 4, maybe pi by 3? Well, let's go ahead and solve it. We have y equals cotan inverse of 1. So cotan of y equals 1. Or 1 over tan y equals 1. Or tan y equals 1, because the reciprocal of 1 is 1. So on the unit circle, where do we have the value 1 from tan y? What angle? The angle pi by 4. Let's try to remember those graphs. Don't look at your notes. Which of the following is the graph of tan inverse? What do you think? A, B, C, or D? Well, it's certainly not C or D. Those are definitely not tan inverse. I won't tell you what those are, but those are not tan inverse. The graph for tan inverse is indeed B. Which of the following do you think is the graph for cotan inverse? Again, don't look at your notes. Give yourself a second. Try to think which one would be the graph of cotan inverse. The answer is A. And one final multiple choice. Which of the following is the graph of cos inverse? Well, it's not A or B because we've already looked at those. But the answer is indeed D. Make sure you look at those graphs and you're confident in identifying the graphs and their inverses. Thanks for watching.